then there is a load. So transmission line modeling is required. Then synchronous machine again. At the power plant, we have the generator, we have the turbine. Turbine is again of uh, various parts, various type of turbines: high pressure turbine, intermediate pressure turbine, low pressure turbine, and other devices are the exciter. So these all plays are the different component of power plant. So when we want to study for different oscillations in the system, it means we have to make the detailed modeling of the system. For having the detailed analysis, we need to have the detailed modeling. For have the analysis introductory part, just to understand the things, we can have the approximate model. So in this unit, we are going to study the model of the synchronous machine. First of all, we will study the model of the synchronous machine, that is in the small, that is the approximate model. And in unit number 1, we will again study the synchronous machine in very much detail. So first of all, we will study the introductory of the synchronous machine model and how to form the model of the synchronous machine, approximate model. So just you see here, just you can see it is a voltage source, synchronous machine, synchronous generator. Because of the rotation of the flux is on the field winding, which is rotatory part, and on the stator there is armature. So when the flux is rotating, how the flux is rotating? Because of the rotation of the turbine shaft, which is rotating the rotor, and thus the flux is rotating. And when the flux is rotating, induced EMF in the armature, that is on the stator, is produced. That induced EMF here is, or you can say excitation EMF, is shown here. Let it be a constant EMF, although it is not a constant, but again let us consider it is a constant EMF. And this is the reactance of the transmission line. Although this reactance is not constant, again we are considering this as a constant. But later on you will see this is also not constant, X reactance of the synchronous machine. And it is a resistance of the winding, or winding. This may be other reactances, maybe of transmission lines, resistance and reactances. So voltage induced here, excitation EMF produced here is given by E is equal to RMS value of the voltage here. E is equal to 4.4 F phi and K omega. Means from here to this 4.4 F phi and K omega. This is the amount of EMF produced. 4.4. You know, we in the synchronous in the electrical machine classes of BTech third year or second year, we study the EMF induced here is given by 4.4 F phi and K omega. K is the winding factor, and omega is the speed, angular speed of the rotor. N is the number of turns in the stator winding. F is the frequency. Phi is the flux. So this is the EMF produced. So this is the RMS value of the voltage produced. When if we want to find out the instantaneous value or maximum value, it is the RMS value. Maximum value will be the under root 2 times of, because it is sinusoidal signal. So maximum value will be under root 2 times of this RMS value. So this is the maximum value. Then actual instantaneous value will be the E is equal to EM sin omega t. EM is the maximum value, amplitude. So E is equal to EM means amplitude under root 2 4.44 F phi and K omega RMS value. So this whole is the amplitude, and it is sin omega t. This is the voltage produced here, instantaneous value of the voltage produced here. And say now this value under root 2 4.4 F phi and let us consider it as a V. So under root 2 V sin omega t is this voltage E. Why we are writing it as a V? Because we know it is RMS value. Total impedance is given by, this is the resistance, reactance of the synchronous machine, which I told let us consider it as a constant, but actually it is not constant. XL is the reactance of the line, net resistance of, so this is the net. Now when the disturbance comes, we know when the disturbance comes here, the current flowing into this will be the voltage. There are two types of current. One is the steady state current, and another is the transient current. The steady state current means when we don't consider the transient, means finally what will happen when the, say, some disturbance has occurred. Disturbance means it may be short circuit, it may be change in reactance, or it may be anything else. Any type of disturbance may be there. So because of that, what will be the net current? Net current will be the this net current. If we consider about the RMS value, then RMS voltage divided by total impedance. So V by Z will be the net current, and instantaneous value of the current will be the instantaneous voltage. That is the under root 2V. This is the instantaneous voltage under root 2V divided by Z, and the power factor angle will be the this you see this under root 2V by Z. If this is the voltage, instantaneous voltage, so this is the current, where this theta will be the power angle. Not power, it is power factor angle. Not, it is different. Power angle is different than the power factor angle. Power angle is the angle between rotating flux, and power factor angle is the angle between voltage and current of the load. So this is power, and this power factor angle is the depends upon this from here. If it is after disturbance, total reactance, if it is a, say, XL plus XM, so tan inverse XY, total tan inverse XYR is the power factor angle. So this theta is this value. Is this clear or not? This is the steady state current. This is the steady state current, means if we don't consider the transient, finally the net current after the disturbance, after any change, net current will be this. Is this point clear up to here? This equation is clear or not?
Yes, sir. Yes, sir.
So this is the steady state current. In addition to that, there is a transient current also. We know what is the transient current. Transient current, we understand that, let us have this. Say this is a voltage source, inductance resistance. As soon as you make the switch on here, what will be the steady state current? Will be the V by R, because in the steady state, in case of a DC, inductance will behave as a short circuit. So current will be V by R. Finally, current will be V by R. That is the IF. Let it be IF. But when you make a switch on, at t equal to 0, current will be 0, because inductor will not allow to flow the current freely. So total current, net current is given by IF is equal to 1 e to minus t L by R. Because here it is a minus t L by R. And where you can say this is IF, and it is IF e to power t L by R. This is natural current, IN. So means this I is given by this. At t equal to 0, current is 0, and finally current will be this V by R. Current will be V by R. That is V by R is equal to IF. So this current IF is the force current, or it is the steady state current, and this is the natural current or transient current. So this is the transient current. The sum of the IF plus this is the total current. Net or some net current is given by this I. So this transient current, if you see this, the shape of this IF e to power t L by R, it will be like this. Here it will be like this. So sum of this plus this will be the net, this current. So it means whenever there is a change, any type of disturbance, there are two current. One is the steady state current, another the transient current, or you can say one is the force current, or another is the natural current. The total current is there, but this natural component of current decay after some time. At when t, let t by L by R is the tau. When tau at t is equal to 0, initially when t is equal to 0, this is equal to 1. Natural current is 1, but when or transient current is equal to IF. when t is equal to infinite, finally it will be 0. Tangent current will be 0. So this component curve, initially it will be high, mean like this high, and finally it will be 0. Okay. Similarly, in case of a capacitor here, you see in case of a capacitor here, the current flowing into this, when you make this switch on, current flowing into this is equal to I e to the power minus I0 to the power t by RC. Means at t is equal to 0, this will be short circuit. Current will behave as a short circuit in DC, and current will be V by R. Finally, when it will be charged, when current is flowing into this, capacitor will going on charge, and finally when it will be charged, this voltage will be equal to this voltage and current will be equal to 0. So net current will be given by like this, I is equal to I0 not RC. So you can say finally current, here final means steady state current or force current, that will be equal to 0. Finally current will be 0, and transient current is this. So total current is also this. So this is the total current, means force current plus natural current, or force current is 0, or you can say steady state current plus tangent current is the net current. So we know in this study we have seen there are two type of current. Whenever the disturbance comes, there are two type of currents. One is the natural component of current, another is the force component of current, or you can say one is the tangent component of current, another is the steady state component of current. And this value of tangent or natural current is given by I is equal to I0 t by tau. दोनों के केस में देखिए यहाँ e to the power minus t by tau, here also e to the power t by tau. इसके केस में RC is the tau, in this case it is L by R is the tau. So total current is given by this. Okay. Now if there is a, so now if okay, before going to that, again come to this. So here you see this is the steady state current. It is a voltage by Z, the steady state current V by Z, and this is power factor angle. And in addition to this, there will be tangent current, since it is a only, you see here in this case there is only reactance and resistance XL, and this total is X and R. Total is X or R, so only inductance is there. So because of that, the transient current will be of this type, A e to the power minus t L by R. जो हमने अभी आपको बताया था, in case of inductance, this is a tangent current. This is a tangent current. When there is a only inductance, then it will be there. When it is a only capacitance, T by tau, in place of tau it will be RC. So total current will be sum of the force current and natural current. So here this is the force net current, and putting the initial condition at t is equal to 0, current is 0. Here you see, put it here. When there is no at t is equal to 0, starting में कोई current नहीं है. Suppose the system is open circuit, at t is equal to 0, it is open circuit. You can say here. So put it here, t is equal to 0. Here t is equal to 0. So we can find the value of A here, and this value of A can you put it here, and finally this equation will be there. This equation will be there, and we can draw this equation like this. Means this is a tangent current. You can say this is a tangent DC current, and this is this steady state current, and sum of this steady state and this tangent is like this. This current means if you see it decays. Finally DC component decays. So this is the net current. Now we have seen. So here in this case you see, when this voltage source is there, which we consider as a, when we this synchronous generator is considered as a voltage source, and this reactance is considered as a constant reactance, then the this is approximate circuit, approximate equivalent model of the synchronous generator, where E excess, E is the excitation voltage produced, and excess, with the help we can describe the model of the synchronous generator in this form. But in fact this X is also not constant. X is not constant. What is the meaning of this? X is not constant. You see here, we earlier also in the previous semester we study. देखिए, there are in the synchronous machine, when we say it is a XS means synchronous reactance, but it is not a synchronous reactance, but actual reactance is the, if you XS is nothing but it is a leakage. There are few other reactances Excess can be the combination of leakage reactance, armature reactance, field winding reactance, and damper winding reactance. There are several winding in the synchronous machine. We simply can't say the reactance is excess because there are different winding in the synchronous generator. In the synchronous generator, when field winding is on the rotor, damper winding is again on the rotor. You can see here, we can see here like this. This is the field winding. Here it is a field winding. Here it is a damper winding. Here it is a damper winding on the rotor, and this is the armature winding. This is the armature winding. So first of all, since there is a air gap, here there is a field winding. Because of rate of change of flux, here induced EMF is produced. But because there is a air gap, so because of this air gap, there is a leakage of the flux. And because against the leakage of the flux, there is a leakage reactance. Here it is a leakage reactance because of this air gap. And this armature is consisting of reactance. It is a armature winding reactance. This winding, reactance of this winding is the field winding, and reactance of this winding is the damper winding reactance. And in fact, when we say, here you see, when we say synchronous reactance is excess, means this only X, XM plus XM is the excess, but it is not excess. Actually, it is a leakage reactance first, and in the steady state, during the disturbance, the field winding and the damper winding also comes into the picture. Damper winding comes into the picture when there is a disturbance, because it tries to damp out the different oscillations. So depending upon the time constant, as you have seen, now again come to this. Again see, depending upon the time, here T by tau, this is a tau, L by R. So depending upon the time constant, L of damper winding is different, L of armature winding is different, L of field winding is different. So depending upon this L, or you can say depending upon this whole time constant, the current decays. Current into the field winding decay, current into the damper winding decay, current into the so in this way you see, depending upon that, here the actual reactance X, when we call it as a excess is axial leakage reactance, or armature winding, field winding, and damper winding are in parallel. This is the net reactance. But this reactance, this is called the steady state reactance. This reactance, this is called the net subtransient reactance, when everything is present. When disturbance is there, subtransient reactance. But depending upon the time constant, first of all, this damper winding decay out. Damper winding time constant is low, so it will be, this current flowing, because of this will be decaying. So only the reactance after some time will remain. After 2-3 cycle, means 50 millisecond or 40-50 millisecond, only this reactance remains, means XL plus in parallel with armature and field winding. And after some time, after 7-8 cycle, this field winding also decay. So this will also be not be there. Then it is called the only XL plus XA. So in the beginning, you can say total reactance XL and all reactances are in parallel. They are called the subtransient reactance. But after removing the damper winding, after decaying of the current into the damper winding, reactance came into the picture is given by this XA plus XF in parallel. This is called the transient reactance. And finally, this field winding, current in the field winding also decay, and XL plus XA. This is called the synchronous machine reactance or steady state reactance. So there are two different reactances. When there are different reactances, so steady state current, if the reactance is throughout the same, so current will be like this. In this, current will be like this, and this current, you can see, this current will be like this. Here, anyway. So current will be E by current will be this. When only Z is there, finally current will be this, and this will be represented by here only this portion, steady state current. But this reactance is changing. In the beginning, the reactance is low because all are in parallel. So this current will be high. Steady state current will be high, or sorry, symmetrical component of current. This will be high. We are not talking about the transient. We call it as a force current or symmetrical component of current during subtransient period. Then after current during transient period, it will be like this. Current finally steady state current will be like this. So this current is at different interval without considering the transient, without considering the natural component. But in fact, the natural component of current is also there. This current is also there. So this should also be added into. This should also be added here. This should also be added. This should also be added. So further this will be modified. So in this way, finally you can say the approximate model of the synchronous machine will be E, which is not constant, it varies, and this axis is also varying. This is the approximate model of the synchronous machine. And now, so is there any question up to now? Jagbir? Hello?
No, sir.
Yes, sir.
Is there any question up to now?
No, sir.
No, sir.
Okay, thank you. Okay, so we have seen the approximate model of the synchronous machine, and this approximate model will be used for different studies. In the short circuit study, it is used. Even in the basic understanding of the SSR, this circuit can be used. But later on, you will see that here actually just I wanted to tell this I told when only inductance resistance are there. This is the time constant quantity L by R. This is the natural component of current. When okay, again go to this. Now, in fact, in the transmission, when the synchronous machine, this synchronous generator is connected to the transmission line, and transmission line not only consists of the resistance and inductance, it also consists of the capacitor. From where the capacitor comes, capacitance is the because of the earth, because the charge present on the transmission line, and because of the presence of the earth, there is a capacitance, and that capacitor is present as a shunt capacitance. But shunt capacitance is also equivalent to the sum of the series component, because we know how to convert star into delta and delta into star. In that way, the equivalent shunt compensation can be made equivalent to the series compensation. But we will describe what is the shunt and series compensation later. But just as a basics, let us consider if there is a capacitor also in the transmission line. There is resistance of the transmission line, inductance of the transmission line, and capacitance of the transmission line. This RLC consists of the resistance, inductance, capacitance of the transmission line, including of resistance, inductance of the synchronous machine. This is also included in this. So now our circuit is like this. Earlier, so far we have seen our circuit is only voltage, resistance, and inductance. But when it is a resistance, inductance, and capacitance also, in that case, the steady state current will be steady state current. So far we have seen it is a V by Z, where Z is equal to R plus J XL. But here now Z is equal to R plus XL minus XC. Now this impedance is the J XL minus XC. So this is a reactance XL minus XC. So steady state current is this, and this can be written as a magnitude. This is a magnitude, and this is the power angle. Is there any question in this? इसमें कोई क्वेश्चन है? इस इक्वेशन में, in this case when there is a RLC circuit, this is a voltage source, then final or steady state current or force current is given by V by this, and this is it power angle. Diksha, is it clear up to now?
Yes, sir.
I think Diksha, okay. So this is there, and this can be written simply. This can be written as Z, and this this power factor angle written as a theta, omega t minus theta, where theta is given by this. This is the steady state current, not actual current flowing into this. Actual current will be this force current plus natural current or transient current. So again, you see, if you see, we have seen here, when there is only inductance and resistance, then it was the natural current, T by L by R, here it is L by R. When there is now, you know, when there is a C and R, then what type of natural current? Now let us have when only inductance and capacitance. When only inductance and capacitance, when some disturbance comes, when some pulse is given into this circuit, only inductance and capacitance, what will be the current flowing into this? Current flowing into this is given by IN. When only pulse is given here, only inductance and only capacitance, when you give the pulse, when there is no resistance, the current flowing into this will be A sin n omega n t, and where omega n is the natural frequency given by this formula 1 by under root LC, where L is this and C is this. Depending upon the value of L and C, there will be frequency. So it means there will be continuous this signal without loss. Since the resistance is not there, so this signal will be produced. This is the concept of oscillator. अगर हमारा LC सर्किट है, उसमें कोई पल्स दे दें तो परमानेंट ये सिग्नल प्रोड्यूस होगा. हमें जिस फ्रीक्वेंसी का सिग्नल चाहिए, ये साइनोसॉइडल सिग्नल चाहिए, उतने फ्रीक्वेंसी उसके अकॉर्डिंगली हम L और C डिसाइड कर सकते हैं. After deciding L and C, we can produce such type of signal, and this signal will be continuously available. Suppose we want 93.5 मेगाहर्ट्ज, तो LOC इस तरह डिसाइड करेंगे, ये सिग्नल हमें कंटिन्यूसली मिलेगा. इफ वी वांट इट 98.3 हर्ट्ज, then accordingly we can megahertz, then accordingly we can decide L and C. But here we are not deciding L and C, we are observing. L and C are only present, but on the basis of L and C, the signal is, this signal is there, means that particular type of frequency signal will be available, and this signal will be available continuously if the resistance is 0. Is there any question up to now? हरप्रीत, इसमें कोई डाउट है, इसमें कुछ पूछना है?
No, sir.
No, sir.
Okay, but in fact there is no system, no device where resistance is not there. There is no pure 100% inductance is available. Whenever there will be inductance, it will also have some resistance. Whenever there is a capacitance, it will also have some resistance. 100% pure capacitor, pure inductor is not available. There is always some resistance into the system. So let us have that resistance is written here R. So this is actual circuit. When there is a actual circuit, in case of a oscillators, we try to minimize this R. That's why we try to give a external source of energy. Here there is no external source of energy. Once you give the pulse, continuously this signal will be available. Here, if you don't give the outer energy, if you give the pulse, the signal will this signal will be available here because of the resistance. Will be available, but here is the IN will not. Here IN is A sin omega n t, but in this case, when this resistance is there, natural component of current will be without source of energy. A is prominent xi omega n t sin omega n t plus psi. This is the natural component of current, and because this xi depends upon the resistance R. If resistance is R, so this xi will be high, and this is because of this e to power minus xi omega n t. This decay is there. Otherwise, this signal has been the continuously uniform signal. So now here this magnitude go on decaying continuously, and finally it can be 0. Finally, no signal will be there. So depending upon the value of xi or depending upon value of resistance, the power factor angle, here it is no power factor, it is sin omega n t. Because of the presence of the resistance, there is power factor angle is also there, and because of the resistance, this e power xi omega n t signal, this component is also there, and because of this component, this is going to decay. If here you see xi is equal to 0, if somehow you can make e to power 0, this signal will be equal to same, and this waveform will be there. Since xi is not 0, xi is having some value of resistance, so signal is like this. This is called the natural component. Here also this is a natural component, and above also this is also a natural component of current, because no outside source of energy. Here there is no source of energy, here there is no source of energy, here also there is no external source of energy, only pulse is given. So that's why this is called the natural component of current. And if somehow you see, if somehow if xi is negative, xi can be negative if R is negative, or later on we will see when we will study SSR, which is the actual topic of this unit, which we will be studying in the next class or so. Then you see when if the xi is negative, when this xi is negative, this will be the minus minus plus e to the power plus something here, e power plus xi omega nt plus. So then the signal will be growing like this. Then signal will be growing. When the signal will be growing, this may can have the problem of resonance. Continuous signal, growing signal is available, which is the abnormal condition of the system. In fact, now again come, our system is here, as I told, system is not only LC, it is a RLC. When there is a RLC system, this will be the natural component of the current. This will be the natural component of the current. So the actual current, now we will come the actual topic, that is the of the unit, that is the subsynchronous resonance. Now you see, this is the signal for current. This is the current. If the disturbance comes in the when the synchronous generator connected with the grid, and the disturbance comes, or disturbances will be always be there. Disturbance into the system, power system is always be there, because there is a sometime the load is connected, sometime load is removed, sometimes some machine, some industry is working, sometimes some industry is becoming off. So there is a change of current, there is change in load. So the disturbance is always there, and that time the current will be given by this I will be the A sin omega nt plus I. This is the steady state current, जो हमने अभी आपको बताया था, steady state current, हरप्रीत अभी बताया था. और this is the natural component of the current, or you can say this is a force current. Finally try to become this, there it is a power frequency. This is power frequency, जो हमारा जो हमने फोर्स लगाया, सोर्स लगाया है. अगर हमारा पावर जो सिंक्रोनस जनरेटर है, जिसका रोटर और जिसका टरबाइन 50 हर्ट्ज पे अगर रन कर रहा है, 50 हर्ट्ज फ्रीक्वेंसी के अकॉर्डिंगली रन कर रहा है, तो वो 50 हर्ट्ज फ्रीक्वेंसी, पावर फ्रीक्वेंसी, उसके अकॉर्डिंगली ये सिग्नल पैदा होगा, स्टेडी स्टेट. एंड दिस इज द ट्रांजिएंट, और यू कैन से नेचुरल कंपोनेंट ऑफ करंट. Means when the disturbance comes, this additional signal will also be there into the system. This additional, where this omega n is the natural frequency. This natural frequency depend upon the components, parameter component of the network, that is depending upon L and C. किसी भी नेटवर्क में L भी होगा और C भी होगा. So depending upon the value of L and C, that is the 1 by under root LC, this natural component will be there. There will be two components. This is the force component, that is called the steady state current. This is natural component of current, which is because of the disturbance in the system. So the total current will be this. Now this current may cause into the problem into the system. This current may cause problem into the system. Now we will study this current in very much detail, and when we study this current, we can say we are going to study the SSR. SSR means subsynchronous resonances. How it is a subsynchronous resonance, and what are its ill effect, that that we are going to study in this chapter. What is the subsynchronous resonance? As the name indicate, subsynchronous. Synchronous means synchronous is taken from the synchronous speed. Synchronous speed means 120 f by p, where you can say it is according to the power frequency. अगर 50 हर्ट्ज का सिग्नल है, 50 हर्ट्ज का पावर फ्रीक्वेंसी है, तो synchronous speed will be 1500 rpm for 4 poles, 3000 rpm for 2 poles. Okay, so that is the power frequency. But subsynchronous मतलब frequency below 50 hertz. And so what is the, if there is a signal of frequency below power frequency is present because of the value of inductance and capacitance is such that, then this is the natural frequency omega n, and this subsynchronous frequency may cause resonance. As name indicates, subsynchronous resonance. It may get resonance with the other signals. This signal can be mechanical signal, this signal can be electrical signal into the system. The whole system is very big. When this system get resonance with other signals available into the system, then the resonance occurs. When this gets complement of that, means it can interact. When this signal interact with the other signal present to the system, then we call it as a resonance. When resonance happens, what is the meaning of resonance? Resonance का मतलब क्या है? When resonance happens, it try to send the power at that frequency, and that may cause the problem into the system. So, is there any, अब तक जो एक्सप्लेन किया है उसके बारे में कुछ पूछना है? So that we can go ahead. इसके बारे में कुछ पूछना है आपको? यस,
नो सर।
संतराम, हाँ देखिए, वी टोल्ड, अब तक हमने क्या बताया? व्हाट इज द फोर्स रेस्पॉन्स, दैट इज द स्टेडी स्टेट रेस्पॉन्स, that is, or you can say what is that frequency omega 0. And another thing we told, natural response or transient response, that is because of this natural frequency, signal of natural frequency. And we told subsynchronous, synchronous, we told subsynchronous, then we described what is the resonance. So before closing this lecture today, can you tell what is the resonance in general? जो हमने जनरली आप सर्किट थ्योरी में जो पढ़ते हैं वो रेजोनेंस क्या होता है, सो दैट नाउ once you understand the resonance, we are able to understand everything in detail about the subsynchronous resonance. So may I ask, what do you understand by the resonance?
सर कैपेसिटिव रिएक्टेंस इज इक्वल, सर कैपेसिटिव रिएक्टेंस जब इंडक्टिव रिएक्टेंस के इक्वल हो जाता है.
Not the कोई अटेंडेंस के लिए तो नया नहीं आया है, all have given the attendance. Okay, so साहिल का लग गया था. तो एनीवे रेजोनेंस का डेफिनेशन आप ठीक से बताओ मिस्टर मोहित.
यस सर.
हाँ, what do you understand by resonance? हाँ, कौन बताएगा? तनु नरवाल बताओ. Define what is resonance.
सर जब एक्सएल और एक्ससी की वैल्यू इक्वल हो जाए सर.
नहीं, अब देखिए आपने पढ़ा होगा कि भाई जब सेना मार्च करती है किसी पुल पे तो समटाइम इट हैपेंस दैट ब्रिज में ब्रेक डाउन, ब्रिज टूट जाता है. उसमें ना तो रिएक्टेंस है, ना कैपेसिटेंस है, ना इंडक्टिव रिएक्टेंस है. तो इंडक्टिव रिएक्टेंस और कैपेसिटिव रिएक्टेंस की बात इलेक्ट्रिकल सर्किट में ही आती है. तो so when I am saying resonance, define in general form, जनरली रेजोनेंस का क्या मतलब है?
Sir,
We are not talking about
impedance
the
and
electrical
inductance
system
cancel
when
to each other.
सर फ्रीक्वेंसी इंक्रीज हो जाएगी
नहीं
जब
नहीं, ये
कोई
तो
भी
इलेक्ट्रिकल
एक्सटर्नल फोर्स,
ये हाँ
फ्रीक्वेंसी इंक्रीज हो
देखिए,
जाएगी सर।
हाँ नहीं तो फिर डेफिनेशन क्या हुई रेजोनेंस की? ये पुल क्यों टूट जाता है जब सेना एक लय में ताल में मार्च करती है और पुल अगर कमजोर है तो टूट जाता है, ऐसा क्यों है? उसमें
Sir,
रेजोनेंस कैसे डिफाइन करेंगे? यस, देखिए ताल ताल कदम की जो फ्रीक्वेंसी है, ताल कदम की जो फ्रीक्वेंसी है वो जब वो ब्रिज की नेचुरल फ्रीक्वेंसी के बराबर हो जाए। ब्रिज की नेचुरल फ्रीक्वेंसी देखो हर एक की नेचुरल फ्रीक्वेंसी होती है, आपको पहले भी बताया था, चाहे मैकेनिकल सिस्टम हो तो 2πm/k, इलेक्ट्रिकल सिस्टम हो तो 1/√LC ओमेगा इक्वल टू 1/√LC। ऐसे ही हाइड्रोलिक सिस्टम है, कोई भी सिस्टम होगा, चाहे मैकेनिकल हो इलेक्ट्रिकल हो, कोई भी सिस्टम होगा, उसकी अपनी एक नेचुरल फ्रीक्वेंसी होती है। आपने 10th में देखा होगा ट्यूनिंग टॉर्क फॉर्क, क्या होता है ट्यूनिंग फॉर्क, क्या कहते हैं उसे? उसको आप जब मारते थे तो उसमें एक फ्रीक्वेंसी पैदा होती थी। 10th में किया है एक्सपेरिमेंट या नहीं किया है? यू 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 शेप का एक ट्यूनिंग फॉर्क होता है, उसको जमीन से मार के ऐसा आवाज निकलती है।
Sir,
तो
oscillation
ऐसे ही
frequency.
उसकी नेचुरल फ्रीक्वेंसी कहते हैं, ऑसिलेशन नहीं, नेचुरल फ्रीक्वेंसी कहते हैं। तो ऐसे ही हर एक की अपनी एक नेचुरल फ्रीक्वेंसी होती है। जैसा आपके घर में कोई बीम है, कॉलम पड़ा हुआ है, उसकी अपनी नेचुरल फ्रीक्वेंसी मीन्स अगर आप उसको कोई भी, आप देखिए आप अपने हाथ में आप गिलास ले लें, प्लेट ले लें, उसको जब आप टर्न थोड़ा सा मारेंगे कहीं तो उसमें एक आवाज निकलेगी, हर एक की डिफरेंट आवाज होगी। गिलास की अपनी आवाज होगी, चम्मच की अपनी आवाज होगी, प्लेट की अपनी आवाज होगी, अपनी साउंड निकलती है। हर एक की अपनी एक फ्रीक्वेंसी होती है डिपेंडिंग अपॉन 2πm/k। एम क्या है, के क्या है, एम और के अकॉर्डिंगली स्प्रिंग कांस्टेंट क्या है, इनर्शिया कांस्टेंट क्या है, उसके अकॉर्डिंगली हर एक की अपनी फ्रीक्वेंसी होती है। ऐसे इलेक्ट्रिकल सिस्टम में भी हर एक की अपनी फ्रीक्वेंसी होती है। तो ये दिस इज कॉल्ड द नेचुरल फ्रीक्वेंसी। इलेक्ट्रिकल में 2π√1/√LC ये इलेक्ट्रिकल फ्रीक्वेंसी होती है। तो जब ये फ्रीक्वेंसी फोर्स फ्रीक्वेंसी के बराबर हो जाए, फोर्स फ्रीक्वेंसी मींस आउटसाइड जो कंपोनेंट लगा हुआ है, जैसे इलेक्ट्रिकल की केस में हमने सोर्स लगाते हैं, जनरेटर लगाया, इलेक्ट्रिकल केस में जनरेटर लगाया, और मैकेनिक जैसे अभी बताया था सेना के केस में जो ताल कदम की अपनी फ्रीक्वेंसी है वो फोर्स फ्रीक्वेंसी हो गई, और ब्रिज की अपनी नेचुरल फ्रीक्वेंसी हो गई उसके एम और के अकॉर्डिंगली। जब ये दोनों फ्रीक्वेंसी बराबर हो जाएं तो रेजोनेंस हो जाता है। और रेजोनेंस होने पे क्या होता है, इट ट्रांसफर द मैक्सिमम एनर्जी एट दैट फ्रीक्वेंसी। तो उस फ्रीक्वेंसी पे ये मैक्सिमम एनर्जी ट्रांसफर करता है। अगर उस समय वो नहीं सहन कर पा रहा है तो ब्रेक डाउन हो जाएगा। दिस इज द बेसिक कंसेप्ट ऑफ रेजोनेंस, चाहे इलेक्ट्रिकल हो या मैकेनिकल हो। इलेक्ट्रिकल के केस में ये कंडीशन आती है, फिर मतलब नेचुरल फ्रीक्वेंसी 1/√LC है और फोर्स फ्रीक्वेंसी पावर फ्रीक्वेंसी, जब दोनों बराबर हो जाए तो रेजोनेंस होगा, तो मैक्सिमम एनर्जी ट्रांसफर करेगा। लेकिन उस टाइम अगर उतने को वो टॉलरेट नहीं कर पाता है तो सिस्टम ब्रेक डाउन होता है। एंड द कंडीशन फॉर दैट इज एक्सएल इजिकल, जब हम इसको सॉल्व करते हैं, एनालिसिस करते हैं, तो एक्सएल इजिकल टू XC आता है। वो कंडीशन है, दैट इज नॉट द डेफिनेशन। It is the condition of resonance, but it is not the definition. Definition is, if the general definition of resonance is, if the natural frequency of the any system equal to the force frequency of that system, at that time it transfer the maximum energy, it exchange the maximum energy, that is called as a resonance. That phenomena is called as a resonance. This is about the resonance. Okay, in the next class we will describe the subsynchronous resonance in detail. Okay, do you have any question now? If you have any question, still you can ask, otherwise we can